So this is the derivation for the expression of heat transfer at constant pressure. So essentially we want to come up with a formula where dH is equal to some value at a constant pressure. And a good place to start would be the definition of enthalpy, where enthalpy is equal to the internal energy plus pressure times volume. So we want to evaluate this equation over an infinitesimal change. So when we want to do that, we essentially follow the formula x plus dx, where x is the original value and dx is the infinitesimal change over a certain boundary. So if we apply this to our enthalpy formula, we will arrive at h plus dh is equal to u plus du plus p plus dp times v plus dv. So I'm just gonna multiply the expressions in the parentheses out, and we get pv plus pdv plus vdp plus dpdv. So this last term is a product of two infinitesimally small values, so this is equal to 0. So now we want to look at the other state function, the function for internal energy. So from the first law, we know that du is equal to dq plus dw. So we can substitute this in to our equation. If you'll notice here, you'll see that we have u and pv. So what you have to recognize is that enthalpy is equal to u plus pv from our first step, u plus pv, which is just the definition of enthalpy. So we can substitute these two terms with h, where h plus dh is now equal to h plus dq plus dw plus pdv plus vdp. So you can see here that the h terms cancel out, and we're left with dh is equal to dq plus dw plus pdv plus vdp. So from earlier, we know that one of our constraints is that the process occurs over constant pressure. This means that dp is equal to 0, and this term evaluates to 0. So we're now left with a dq plus dw plus pdv. So regarding the dw term, if we assume that the process is in equilibrium and that the work of expansion is reversible, then we know that dw is equal to negative p dv, and we can substitute that into our formula. Now these two terms cancel out, and we're finally left with dh is equal to dq at constant pressure. If we want to integrate or evaluate the integral, we can just do this at the same initial and final positions and see that delta h is equal to q at constant p. And this is the derivation for heat transfer at constant pressure.